Before creation, there was nothing but an infinite, restless void, a silent, expanding darkness waiting to ignite. What emerged from that chaos would shape every shadow, every breath, every heartbeat. Close your eyes and imagine the silent darkness before the first stars were born. No galaxies glittered, no planets turned on their axes, just an expanding void still carrying the shockwaves of its explosive beginning. Now open them and look around. You see a universe filled with light, structure, and life. The atoms making up your body, the air you breathe, and every star illuminating the night sky emerged from that ancient darkness. Today, we trace the story of how those atoms, born in the infancy of the cosmos, built everything we know. Picture the universe as it was moments after the Big Bang. Temperatures beyond comprehension, energy so dense that matter and light intertwined in a roiling sea of particles. In these fleeting instants, protons and neutrons didn't yet exist in stable forms. Only their fundamental building blocks, the quarks, drifted in a fiery plasma. Then, as the universe expanded, the heat eased just enough for quarks to assemble into protons and neutrons. It took less than a second, but it set the stage for everything to come. Within minutes, these protons and neutrons fused into the very first atomic nuclei, mainly hydrogen and helium, plus a dash of lithium. Then the cosmos entered a prolonged cooling phase. For nearly 380,000 years, electrons roamed freely, scattering light in every direction. The universe was opaque, an immense fog of radiation. Finally, as expansion continued, the temperature dropped further, allowing electrons to bind to nuclei. This moment is sometimes called recombination, but in truth, it was the first real combination. Suddenly, atoms existed, and the cosmos became transparent. Light could now travel unimpeded, leaving behind a fossil glow known as the cosmic microwave background, the earliest picture we have of our universe. Yet in those early epochs, the universe looked almost uniform, an ocean of hydrogen and helium gas, spread out across unfathomable distances. How did it go from that stark simplicity to the dazzling diversity of galaxies and stars we see today? The answer lies in tiny fluctuations, small irregularities in density imprinted at the dawn of time. Gravity, relentless in its pull, amplified these pockets of slightly denser gas. Over hundreds of millions of years, they collapsed into massive clouds. Under the immense pressure at their centers, hydrogen atoms began to fuse, releasing energy that ignited the universe's first stars. With the emergence of stars, the cosmic landscape transformed. These new lights in the darkness began to fuse hydrogen into helium, blazing with the power of nuclear fusion. Over their lifespans, large stars progressed to fuse heavier elements: carbon, oxygen, neon, silicon, all the way up to iron. But forging elements heavier than iron requires energy input beyond what stellar cores can typically supply. That's where supernovae come in. When particularly massive stars die, their cores collapse and unleash titanic explosions. In those cataclysmic moments, the shock waves push atomic nuclei together with ferocious force, creating elements like gold, silver, or uranium. These heavy atoms, once ejected, enrich the surrounding gas, seeding future generations of stars and planets with a richer assortment of ingredients. But the story doesn't end with atoms forming. Just wait until you uncover how they conspired to forge everything we know, and perhaps everything we fear. As cosmic time marched on, galaxies formed around clumps of dark matter, an invisible substance that does not emit or absorb light, but exerts gravitational influence. Though we can't detect dark matter directly, its presence is inferred from the way galaxies rotate and cluster. It's as though each galaxy has a hidden skeleton of dark matter that scaffolds normal, visible matter into place. Within these galaxies, star formation occurred repeatedly in waves. Stars lived, died, and redistributed elements into interstellar clouds. These clouds birthed new stars, which in turn produced more heavy elements, further diversifying the cosmic chemistry. From this grand cycle, planetary systems arose. Dust grains stuck together, forming larger and larger bodies until planets emerged. Our own solar system is part of that legacy. The iron in Earth's core, the oxygen we breathe, the carbon in our cells, all owe their existence to generations of stars that lived and died long before our sun even formed. It's a profound realization. Every atom in your body has traveled across eons, passing through cosmic processes that molded the universe we inhabit. Yet for all its brilliance, normal matter, the stuff of atoms, accounts for only about 4% of the total contents of the cosmos. Around 26% is dark matter. The remaining 70% is something even more mysterious. Dark energy, a form of energy permeating space that accelerates the expansion of the universe. While these hidden components do not directly alter the atomic story, they shape the universe's large-scale behavior, influencing how galaxies move apart and how structures evolve over billions of years. Over time, astronomers and physicists uncovered puzzles in this tapestry. For instance, the amount of lithium predicted to form in the early universe is higher than what we observe in ancient stars. Some mechanism, perhaps unknown nuclear reactions in stellar interiors or other exotic physics, seems to be destroying or relocating lithium. Then there's the antimatter problem. The Big Bang should have produced matter and antimatter in equal amounts, but only matter remains in abundance. What subtle asymmetry tipped the balance, ensuring atoms won the day? Such mysteries remind us that our grand narrative, though well supported in its broad strokes, is incomplete. We continue to refine cosmic models, searching for hidden details that might resolve these discrepancies. New telescopes and observatories peer deeper into space and further back in time, capturing the feeble glow of the first galaxies. Meanwhile, particle accelerators on Earth recreate mini-versions of the Big Bang's conditions, probing the behavior of quarks and gluons at extreme energies. These complementary approaches, studying the very large and the very small, yield a more unified picture of how atoms shape reality. Consider also neutron star collisions, which we now know contribute to the production of heavy elements. When two neutron stars spiral together, they merge in a burst of gravitational waves and high-energy ejecta. Observations suggest these events can synthesize large amounts of elements like gold and platinum. That means the jewelry on your hand or the electronics in your device may owe part of their atomic ancestry to the collision of dead stars, an almost surreal testament to the interconnectedness of cosmic processes. Though vast and often inscrutable, the story of how atoms built the universe resonates on a personal level. It tells us we belong to a chain of events spanning nearly 14 billion years. We are each living expressions of a universe that crafts and recycles its own materials across epochs too grand for us to fully imagine. The atoms that first formed in the Big Bang still exist, now woven into everything from distant galaxies to the structure of your very bones. And across those countless transformations, from quarks binding into protons to stars forging elements and supernovae hurling them into space, matter never stopped evolving. When you next look up at the stars, consider the hidden connections binding you to them. The same cosmic alchemy that set them ablaze also set the conditions for life on Earth. That is the saga of atoms, born in fire, nurtured in the hearts of stars, scattered through supernova blasts, and reassembled into living, thinking beings. It is a testament to what nature can accomplish when given enough time, a quiet marvel woven into every breath we take. Now, let us take a closer look at the universe just after recombination, when the first atoms formed and the cosmic microwave background spread across all directions like a newborn photograph of creation. At that stage, much of space appeared dark to any hypothetical observer. With no stars burning yet, an entire epoch called the Dark Ages stretched from roughly 380,000 years after the Big Bang to about 200 million years later. During this dim interval, hydrogen and helium gas drifted in enormous clouds, cooled gradually, and began to feel the gentle nudge of gravity. Imperceptibly at first, then with growing momentum, these clouds collapsed into denser regions that would become cosmic nurseries for the earliest stars. Scientists used powerful computers to simulate how these dark age clouds formed filaments and knots, creating intricate networks, sometimes referred to as the cosmic web. Filaments of hydrogen and helium gas, along with dark matter scaffolding, funneled material into the knots where proto-galaxies started to emerge. The presence of dark matter was crucial here. Even though it doesn't interact electromagnetically, its gravity helped shape where visible matter accumulated. Without dark matter's gravitational influence, our early universe might have stayed a more uniform, featureless expanse for a much longer time. Instead, these unseen halos gathered enough mass for the temperature and density in certain pockets to rise, and that is where the spark of fusion would eventually ignite. Once these proto-galaxies reached sufficient densities, some pockets collapsed to create the universe's first stars, often called population 3 stars. The name might sound odd. Modern astronomy labels the oldest stars as population 3, while stars like our Sun are population 1, and intermediate age stars are population 2. But naming conventions aside, population 3 stars remain a subject of intense study and speculation. They likely formed from nearly pristine hydrogen and helium with almost no heavier elements. Because heavier elements help gas clouds cool more efficiently, these first stars might have been exceptionally massive, hundreds of times heavier than our Sun. Their lives were short and furious, fusing hydrogen into helium at breakneck speed, pushing nuclear reactions as far as they could go, then dying in colossal supernovae that seeded their surroundings with the first real batch of metals, elements heavier than helium. If you are amazed by how much is still left to uncover about these primordial stars, consider subscribing to stay updated on the latest discoveries and theories in cosmology from Frontiers of Infinity. Population 3 stars, despite being the true pioneers of stellar evolution, remain elusive to direct observation. We search for their fingerprints in the earliest galaxies, hoping to detect the chemical aftermath they left behind. Telescopes like the James Webb Space Telescope may one day spot halos of pristine gas or faint cosmic signatures revealing these ancient behemoths. If found, they would be among the brightest beacons to ever grace the infant universe. Yet ironically, they also represent a past so distant that their light is stretched and dimmed across billions of light-years of travel. Following the Dark Ages and the birth of those first stars, a new epoch took shape, the era of Reionization. As these early stars and their successor generations began shining, their intense ultraviolet radiation ionized the neutral hydrogen in surrounding regions, stripping electrons from atoms once more. This process carved out transparent bubbles of ionized gas in an otherwise neutral cosmos. Over time, these bubbles expanded and eventually overlapped, clearing the universe of its neutral hydrogen fog. By the end of Reionization, light could travel across vast distances, and galaxies as we know them started to take on the shapes we see in deep astronomical images. Galaxies did not just appear in isolation, though. They often formed in clusters or superclusters, bound by gravity into vast chains and walls, spanning hundreds of millions of light-years. Within these structures, stars formed in waves, some small, some gigantic, each generation adding elements to the cosmic mix. This is how the universe's chemical diversity gradually blossomed. Where once there were only hydrogen, helium, and faint traces of lithium, there now emerged carbon, nitrogen, oxygen, and a host of other elements that open the door to complex chemistry and eventually life. Amid this swirling drama, black holes also had their moment. The gravitational collapse of massive stars sometimes leaves behind black holes, regions so dense that not even light can escape. In young galaxies, supermassive black holes could form at the centers, possibly through the mergers of many smaller black holes, or the direct collapse of colossal gas clouds. These monsters power quasars, exceedingly bright beacons that outshine entire galaxies. Quasars served as another major milestone in cosmic evolution, pumping radiation across the universe and influencing the environment in which galaxies grew. As billions of years passed, stars kept forging heavier elements, and supernova explosions scattered them outward. Through countless cycles of stellar birth and death, the universe evolved into a place of increasing complexity. Vast spiral galaxies like the Milky Way and elliptical giants like M87 acquired distinct shapes, star clusters, and planetary systems. Within the Milky Way, around 4.6 billion years ago, one particular cloud of gas and dust coalesced to form our Sun and its retinue of planets, asteroids, and comets. The Earth, nestled at a comfortable distance from the Sun, became a crucible for even greater chemical intricacy: life itself. In the grand scheme, the emergence of life on Earth is a relatively recent development, but its foundation rests squarely on the cosmos's earlier history of nucleosynthesis. Without heavier elements, carbon, nitrogen, phosphorus, and so on, complex biomolecules could never form. And so the story of atoms building the universe is simultaneously the story of atoms building us. When we say we are stardust, it is not just poetic flourish, it's a literal truth about our constituent matter. Yet all of this wondrous complexity unfolds in a broader context, an expanding universe dominated by dark energy. Once astronomers believed cosmic expansion would eventually slow and possibly reverse under gravity's pull. But the late 1990s brought a surprise. Distant supernovae appeared dimmer than expected, suggesting they were farther away than our models predicted. Dark energy, a mysterious force accelerating the expansion, had to be factored in. Today, dark energy accounts for about 70% of the universe's total energy budget, overshadowing both normal matter and dark matter. Its exact nature remains one of the deepest puzzles in cosmology. Is it a property of the vacuum itself, a field permeating space, or something we have yet to conceive? Still, in galaxies, local gravity triumphs over cosmic acceleration on small scales. Well, small in cosmic terms. Stars in the Milky Way remain bound to our galactic center, and the Sun's gravitational hold keeps Earth close. These nested realms of structure, stars, planets, clusters, carry on their intricate dance, even as the space between distant galaxy clusters stretches further apart with each passing epoch. With each new observation campaign, we refine our understanding of this evolution. Projects like the Sloan Digital Sky Survey map out galaxy positions, revealing a filamentary cosmic web that reaffirms the power of tiny quantum fluctuations from the universe's earliest moments. Spectroscopic surveys decode the chemical fingerprints in starlight, showing us which elements are abundant and offering clues to a star's age. Meanwhile, gravitational wave detectors pick up the tremors of colliding black holes and neutron stars, providing a fresh window into violent cosmic events that produce or destroy heavy elements. This evolving tableau of matter, energy, and cosmic expansion underscores how pivotal atoms truly are. They are the carriers of structure, the seeds of chemistry, and the foundation for everything tangible. From the perspective of quantum mechanics, atoms are mostly empty space with nuclei and electron clouds. Yet, from a cosmic perspective, their role in forging stars and galaxies is monumental. Because they can combine and recombine under changing conditions, they enable an ever-evolving universe, one that transitions from simple hydrogen gas to the cornucopia of elements we see around us. The scope of this transformation can sometimes distract us from the humbler but no less remarkable reality. Most of the atoms in the early universe were hydrogen. That hydrogen remains the most abundant element, fueling stellar fusion across billions of years. The bright skies we witness on a clear night are a testament to hydrogen's fusion in countless stellar cores, shining across space-time. It is both reassuring and awe-inspiring to know that after all these epochs, Hydrogen still traces its lineage back to the first moments of existence, carrying echoes of the cosmos's original fire. In this dynamic interplay of forces and elements, we find a universe that is not static, but alive with processes that have shaped it through time. Our own existence exemplifies that cosmic legacy, a living testament to how atoms built the universe, forging the scaffolding for planets and biology alike. The same processes that once created the first helium nuclei now act in your body as you breathe, metabolize, and think, albeit on a more intricate biochemical level. If that doesn't kindle a sense of marvel, it's hard to imagine what would. And yet, we have miles to go. Questions about dark matter, dark energy, the fate of the expanding universe, and the origin of cosmic structures persist. Each new discovery peels back another layer, showing us the delicate balance that allowed atoms to become the architects of galaxies and life. The more we learn, the more we see that the cosmos is anything but random. It's governed by fundamental laws that permit mind-boggling complexity to bloom from simple beginnings. In that realization, we discover our own place in the cosmic narrative, woven from threads of starfire and cosmic dust. Moving from the broad strokes of cosmic evolution, let us delve deeper into how these atoms and forces sculpted the structures we see today. By the time our universe reached about 1 billion years old, galaxies were forming in earnest. Some took on graceful spiral arms, like our Milky Way, while others became denser elliptical clusters, often found at the centers of galaxy groups. Spiral galaxies, in particular, presented an ideal environment for ongoing star formation, as their rotating disks funneled gas into new stellar nurseries. With every passing epoch, these galaxies assembled larger collections of stars, many of which would eventually enrich the interstellar medium with heavier elements upon their deaths. An often overlooked aspect of this period is the role of merging galaxies. Larger galaxies frequently swallowed up smaller ones, incorporating their stars and gas. In the process, collisions could ignite starbursts, rapid, intense episodes of star formation triggered by the turbulent mixing of gas. Over cosmic time, these mergers shaped the grand-scale architecture of the universe. Massive galaxy clusters and superclusters bound together by invisible strands of dark matter. Within these sprawling structures, the interplay of gravity, gas dynamics, and feedback from supernovae all conspired to produce the tapestry of galaxies that fill our cosmic panoramas. The heart of many galaxies features a supermassive black hole, millions or even billions of times the mass of our Sun. The genesis of these behemoths remains a topic of active research. Some hypothesize that they formed from the direct collapse of enormous gas clouds in the early universe. Others suggest they grew from repeated mergers of smaller black holes formed by the collapse of giant stars. Whatever their origin, these gravitational giants heavily influence their host galaxies, occasionally consuming swaths of gas, flaring as active galactic nuclei, and sometimes blasting out jets that can heat or disperse interstellar gas. In doing so, they regulate how quickly stars are born, effectively controlling the pace of atomic transformation within their galactic domains. We might consider our own Milky Way a relatively quiescent spiral, at least by the standards of more active galaxies. Yet it too has had its share of mergers with smaller dwarfs, and its central black hole occasionally dines on stray clouds of matter. Meanwhile, spiral arms continue to generate new stars at a modest rate, fueled by gas left over from previous generations and occasional infusions from satellite galaxies. In this way, the Milky Way serves as a living laboratory of atomic cycling. Stars condense from interstellar gas, create heavier elements via fusion, and often end their lives scattering that processed material back out into the galactic medium. If these colossal forces at the hearts of galaxies intrigue you, consider sharing this episode with a friend who appreciates the hidden engines that shape our cosmic neighborhood. Turning our attention to planetary systems, each star that forms in a gas-rich environment can gather a swirling disk of debris around it. In these protoplanetary disks, dust grains composed of heavier elements collide and stick together. Over time, they form larger aggregates, pebbles, rocks, and ultimately planetesimals. As gravity grows stronger in these budding objects, they pull in more material, defining the architecture of a new solar system. The composition of these planets depends on what elements are abundant in the disk. Rocky worlds like Earth form closer to the star where it is warmer, while gas giants form farther out, capturing lighter elements like hydrogen and helium. This distribution underscores how atoms, in varying combinations, create an astonishing range of planetary outcomes. In our own solar system's case, Earth lies in a region sometimes called the Goldilocks zone, neither too hot nor too cold for liquid water to persist on the surface. And that water, once again, owes its origin to hydrogen synthesized in the Big Bang and oxygen forged inside stars. The same goes for life-essential carbon, nitrogen, and phosphorus. In other words, the cradle of our biosphere is fundamentally a product of cosmic cycles traced back across countless millennia. Such reflections naturally lead to the question of life beyond Earth. The atoms that built our planet, particularly those heavier than helium, should be present in countless other star systems. Indeed, exoplanet surveys confirm that rocky worlds, gas giants, and everything in between appear to be common throughout the galaxy. If biochemistry can emerge whenever conditions are suitable, the universe may teem with planets harboring their own evolutionary dramas. While we have yet to find definitive proof of life beyond our planet, the cosmic abundance of atoms crucial for complex chemistry strongly hints that Earth's case might not be unique. Viewed on the largest scale, the cosmic web extends across hundreds of millions of light-years. Filaments of dark matter and luminous galaxies intertwine, leaving vast voids of near-total emptiness. Within the denser knots of this web, galactic clusters appear, some containing thousands of galaxies, each swirling with billions of stars. The atoms in these galaxies are not static. They cycle in and out through star formation, supernova explosions, and the infall of intergalactic gas. In cluster environments, galaxies can be stripped of gas as they plow through the hot intracluster medium, further shaping how atoms congregate and evolve. Every region of space, from the smallest dwarf galaxy to the mightiest supercluster, participates in this grand recycling. As we zoom back in on Earth, we're reminded that our planet is not just a passive recipient of cosmic bounty. Over its 4.5 billion-year history, Earth has undergone transformations that continue redistributing atoms across continents, oceans, and the atmosphere. Plate tectonics recycles crustal materials, volcanic eruptions release gases into the sky, and biological processes lock carbon into sediments or release it back into the air. Even now, the atoms that once formed ancient organisms might reside in your body, highlighting that the cosmos is not the only scale at which matter circulates in mesmerizing ways. In fact, consider that the journey of an atom might span multiple scales. Born in a supernova, it becomes part of interstellar dust, travels through a protoplanetary disk, ends up in Earth's crust, emerges via volcanic activity, enters the ocean, gets incorporated into a living organism, and is eventually exhaled or otherwise returned to the environment, only to continue its odyssey. Though we often think of ourselves as separate from cosmic events, these ongoing exchanges illustrate how the border between space and life is less rigid than we typically assume. The more we comprehend this interconnectedness, the more pressing certain questions become. Why did the universe allow for such intricate chemistry and structure? Was it inevitable that matter would organize into galaxies, stars, planets, and even consciousness? Is there a deeper cosmic principle at work? Or is it simply the outcome of basic physics playing out over eons? Cosmologists and astrophysicists attempt to answer these questions using tools like cosmic inflation theory, which explains how the universe grew exponentially in its first fraction of a second, ironing out irregularities, yet seeding the small density variations that later grew into galaxies. They also use observational surveys to measure the cosmic microwave background with exquisite precision, gleaning clues about the universe's shape, composition, and the distribution of dark matter. Each breakthrough peels back another layer, revealing how delicate the balance is. If certain fundamental constants were even slightly different, atoms might never have formed in stable configurations, or stars might burn out too fast to enrich the universe with heavy elements. It is in these delicate alignments that some find reason to contemplate philosophical or even spiritual interpretations of cosmic history. Others focus on the empirical puzzle, a set of physical laws that appear precise enough to permit complexity, yet flexible enough to allow for astonishing variety. Either way, the existence of atoms and their propensity to assemble into rich structures remains a central riddle and a central wonder. Returning to the timeline of atomic evolution, one might note that the universe is still young on grand cosmic timescales. Stars will continue to form for trillions of years, albeit at a declining rate. Eventually, the cosmos might move into a future era where star formation dwindles, galaxies grow dark, and black holes dominate. Even then, the atoms we cherish now, hydrogen, helium, carbon, oxygen, may persist in some form, locked away in cold debris or slowly captured by black holes. The cosmic story is far from over. We are merely in one of its luminous, star-filled chapters. For us, in this particular moment, understanding how atoms built the universe serves as both an intellectual journey and a reminder of our heritage. Every cosmic phenomenon, from swirling galaxies to the fleeting flicker of a shooting star, testifies to a universe that transforms, recycles, and evolves on every scale. The more we study these processes, the more we realize that existence is an unbroken continuum of atomic migrations, stretching back to the Big Bang and reaching forward into horizons we have yet to imagine. So, while it can be easy to focus on daily life's minutiae, there's value in stepping back to see our place in this cosmic dance. We are children of hydrogen and helium, shaped by the fires of stellar fusion, enriched by supernova blasts, and woven into a tapestry of orbits and cycles. That realization can be both humbling and empowering. Humbling because we occupy a single world in a vast expanse. Empowering because we carry inside us the very matter that once lit the primordial skies. In the end, the story of atoms building the universe is our story too. An odyssey of particles journeying through infinite possibilities, binding themselves into new forms, and, in at least one corner of the cosmos, awakening to their own origins. That awakening, and the curiosity it sparks, may be among the finest gifts the universe has offered itself. Earth's earliest chapters began with chaos, a young star system shrouded in clouds of gas and dust left over from older stellar generations. As the sun ignited, the surrounding disk evolved through a series of collisions and consolidations, eventually producing a family of planets, moons, and smaller bodies. Among them was our Earth, a molten sphere pummeled by impacts, bombarded by solar radiation, and only tenuously protected from the vacuum beyond. Over time, as heavier elements sank into its core and lighter materials formed a crust, oceans and an atmosphere emerged. The atoms that once drifted through interstellar space, oxygen, carbon, nitrogen, and more, now played critical roles in forming molecules essential for geological and biological processes. Later in this video, we'll unravel the haunting truth of how atoms wield the power to ignite life, or extinguish it. Stay tuned. At first glance, life might seem to have arisen by chance. Yet look closer, and you see a chain of cosmic continuity. Carbon, fashioned in stellar interiors, pairs with hydrogen and oxygen to form countless organic compounds. Simple molecules like methane, ammonia, and water can exist in suitable environments, occasionally receiving an energetic jolt from lightning or volcanic activity. In such conditions, molecules can link into increasingly complex arrangements. Modern experiments attempt to replicate these early pathways, sparking chemical soups to observe whether they yield amino acids or other building blocks of life. The results hint that, given enough time and the right environment, atoms naturally push toward complexity. Even so, how life ignited on Earth remains partly shrouded in mystery. Did the key ingredients form here in volcanic vents or shallow pools? Or were they delivered by comets and asteroids carrying organic compounds? The cosmic perspective allows for both. Comets are effectively icy time capsules, preserving a record of chemistry that traces back to the solar system's birth. Asteroids, especially carbon-rich ones, can harbor complex organics forged in interstellar clouds. When these celestial messengers impacted the early Earth, they may have sprinkled the planet with vital seeds. Whether that was the decisive trigger or just one contributing factor, it underscores the idea that life and cosmic matter are inexorably linked. Beyond Earth, we search for similar patterns across the galaxy, intrigued by worlds like Mars, once warmer and wetter, or ocean-bearing moons such as Europa and Enceladus. Atoms, guided by familiar chemistry, could lay down the same foundations there that they did on Earth. The difference might be environmental constraints, temperature, radiation, geological activity, that determine whether complex life can take hold. Yet the cosmic supply of raw materials appears abundant. In principle, if conditions align, the interplay between hydrogen, carbon, oxygen, and other elements might birth life far from here. As we explore these possibilities, we're reminded that atoms form the bedrock of all known biology. DNA, for instance, is a molecular chain encoded with life's blueprint, reliant on carbon, hydrogen, oxygen, nitrogen, and phosphorus atoms arranged in precise configurations. Change one small aspect of those atomic bonds, and the entire structure could fail. This intricate reliance on the details of atomic chemistry reveals just how fragile and yet how powerful life can be. Minute changes at the atomic level can spawn vast differences in organisms, ecosystems, and evolutionary paths. Meanwhile, our ability to observe the cosmos hinges on atoms as well. The photons leaving a star carry spectral signatures of the elements in its atmosphere. When we use spectroscopes, we decode these signatures, effectively reading the cosmic barcode of hydrogen, helium, iron, or any other element present. These patterns tell us about a star's temperature, luminosity, and even subtle shifts that might indicate orbiting planets. Without the distinct ways in which atoms absorb and emit light, much of modern astronomy would be blind to the actual composition of distant worlds. Our eyes, telescopes, and detectors all rely on the consistent rules of atomic physics to unravel the galaxy's secrets. Consider, too, the technological implications of our deepening knowledge about atoms. From nuclear fusion research, seeking to replicate stellar energy production on Earth, to quantum computing, leveraging the unique behaviors of electrons and photons, humanity is extending cosmic principles into practical applications. These endeavors serve as reminders that the processes forging the universe's grand vistas can also fuel progress in labs and factories. Atoms can release formidable energy when split, nuclear fission, or fused, nuclear fusion, powering entire cities if harnessed correctly. That same power can be destructive as well, highlighting the dual-edged nature of atomic mastery. In a similar vein, we owe the electronics revolution to the manipulation of electrons in semiconductor materials, again, an atomic-level phenomenon. Silicon chips, doped with precise amounts of other elements, allow us to build vast networks of information transfer. By controlling how electrons move through these silicon lattices, we create digital logic, the very backbone of computers, smartphones, and our interconnected world. So, the cosmic journey of atoms isn't just academic. It shapes our daily reality, from the steel in our cars to the copper wires in our devices. The more we learn about atoms, the more we realize their universality. Whether they reside in the core of a supergiant star or form part of a microchip on Earth, they follow the same fundamental laws. Electromagnetism holds electrons in orbit around nuclei. The strong nuclear force binds protons and neutrons together, and quantum mechanics governs their energies and transitions. It's the interplay of these forces that yields chemical bonds and, in turn, the boundless varieties of matter we encounter. All of these points steer us back to a central theme: the formation, distribution, and rearrangement of atoms is a story that transcends individual worlds. It encompasses the birth of stars, the forging of galaxies, the emergence of life, and the rise of civilization. Any phenomenon we see, from glowing nebulae to coral reefs, owes its existence to atoms dancing to the tune of physical laws. Even though dark matter and dark energy loom as great unknowns, they do not negate the critical part atoms play in structuring the visible cosmos. Subtle questions linger. Could there be forms of matter or energy that do not conform to the same principles we observe? Are there exotic phases of matter in neutron stars or around black holes that stretch atomic stability to its limit? Ongoing research in high-energy physics and astrophysics seeks to probe these extremes. Each time we push the boundary, we confirm just how universal atomic laws seem to be, and how bizarrely they might manifest under extreme conditions. In neutron stars, for instance, matter is so dense that electrons and protons can fuse into neutrons, creating a material akin to a giant atomic nucleus the size of a city. In that sense, the history of atoms building the universe is also the history of boundaries being tested, from the earliest days when particles could barely exist, to star interiors where atoms are forged or broken, to the black holes where matter might be crushed to a state beyond our current understanding. Each environment tells a tale of how fundamental particles respond to heat, pressure, and gravitational forces. And each environment adds another layer to the tapestry, guiding atoms along new pathways of cosmic evolution. Looking ahead, we can anticipate more surprises. As we upgrade our observatories, both on Earth and in space, we'll glean better insights into the primordial universe, the era of the first stars, and the dynamic interplay of galaxies across cosmic time. Missions poised to retrieve samples from asteroids and comets might further illuminate how interplanetary material has shaped planetary surfaces, possibly even delivering vital compounds for life. The saga of atoms is not static. It continues unfolding with every fresh measurement, every newly launched telescope, and every collaborative effort among astronomers, physicists, chemists, and biologists. In this grand perspective, we stand as participants in a cosmic chain of creation. Our curiosity to explore, analyze, and understand is itself an outcome of atomic processes that built our nervous systems and brains. From quarks binding in the first instant to the forging of heavy elements in supernovae, the entire storyline pulses through us. Such awareness can shift how we see our place in the universe. We're not mere observers. We're an expression of its fundamental narrative, linked by the common thread of atoms that emerged long before our sun had even flared into being. Turning our attention to the present-day universe, we see that much has changed since those first stars ignited. Galaxies have matured, some evolving into graceful spirals, others merging into gigantic ellipticals, and many smaller, irregular forms scattered throughout. In any given galaxy, billions to trillions of stars fill the void with light, while countless planets, asteroids, and comets orbit in the shadows. The cosmic web linking these galaxies is now thoroughly mapped in places, revealing vast filaments where matter congregates and near-empty voids spanning enormous distances. Amid this structure, atoms continue their quiet, methodical work of assembling new configurations. Stars are still forming in nebulae, cosmic clouds teeming with gas and dust, while older stars approach their ends, ready to recycle their material back into the interstellar medium. At larger scales, galaxy clusters tug on one another, occasionally crashing together in violent collisions that release tremendous energy. These cluster mergers can spawn shockwaves stretching millions of light-years, heating gas to extreme temperatures and illuminating how matter moves on colossal scales. When we zoom in on individual galaxies, we find pockets of vigorous star formation known as starburst regions. These bursts often happen after some event, like a close encounter with another galaxy, jostles dense clouds of gas, compressing them into new stellar nurseries. Within these nurseries, dust grains coated with organic molecules can come together to form rocky cores for budding planets. The starlight that eventually emerges from such a region carries the spectral signatures of whichever elements happen to be abundant in its environment, offering astronomers a clue about its chemical history. Meanwhile, in some galaxies, the central supermassive black hole enters an active phase, drawing in swirling disks of gas that radiate intensely across the electromagnetic spectrum. These active galactic nuclei can briefly outshine all the stars in their host galaxy, fueled by atoms funneling into the black hole's immense gravitational well. As material spirals inward, friction and magnetic fields heat it to extreme temperatures, producing blasts of energy that can alter star formation thousands of light-years away. Even in these extreme environments, the rules of atomic physics remain the same. Electrons transition between energy levels, photons are emitted, and ionized gas interacts with magnetic fields. Human observation of these cosmic happenings depends on the fact that photons, which travel across vast distances, eventually reach our instruments on Earth or in orbit. In principle, the oldest stars and galaxies remain visible to us if their light has had enough time to span the cosmic gulf. Yet because the universe expands, their wavelengths get stretched. This is the redshift that Edwin Hubble first identified when studying distant galaxies. The higher the redshift, the more ancient the source. By peering at objects with extreme redshifts, we effectively glimpse epochs when atoms were assembling the earliest luminous structures. These observations form the backbone of modern cosmology, verifying theories about how atoms shape the cosmos. When telescopes like Hubble or JWST capture faint galaxies from over 13 billion years ago, they let us see a universe in its infancy. We notice simpler chemical compositions, strong star formation, and sometimes early hints of supermassive black holes. It's as if we're watching an old home movie of the universe, witnessing how matter organized itself when galaxies were just beginning to mature. Every new detection refines our timeline, revealing details about how quickly heavier elements appeared and how stars influenced their surroundings. Notably, this incremental unveiling of cosmic history also enhances our grasp of dark matter and dark energy. The distribution of galaxies at different epochs helps us infer how much dark matter was present in the early universe, because we see how quickly structures formed. Meanwhile, the expansion rate at different times indicates how strongly dark energy has affected the universe's growth. In that sense, the evolution of atoms, where, when, and how they coalesced into galaxies, ties directly to these hidden components that govern the cosmic stage. Although invisible, dark matter and dark energy leave their fingerprints on how quickly or slowly atoms congregate into luminous forms. Don't miss what's coming next. Hit subscribe and join us for the next chapter of this cosmic journey. On Earth, our scientific pursuits continue to push boundaries. Particle accelerators slam atomic nuclei together at near-light speeds, giving a fleeting glance at the conditions reminiscent of the early universe. High-energy experiments probe the quark-gluon plasma, a state of matter that likely dominated the cosmos in the first microseconds post-Big Bang. By studying how these particles behave, we glean insights into how protons and neutrons first coalesced, and why the universe favors matter over antimatter. Such work is painstaking, but each discovery links directly to fundamental cosmological questions about why atoms prevailed and how they built everything we see. In parallel, astronomers refine measurements of cosmic microwave background radiation to a precision unimaginable decades ago. Minuscule fluctuations in this faint glow encode information about the ratio of normal matter to dark matter, the geometry of the universe, and the seeds of structure formation. This data acts like a cosmic birth certificate, and the details recorded there match closely with theories describing how atoms, just a few minutes old at the time, formed helium and other light nuclei in the process known as Big Bang nucleosynthesis. Those same theories predict the abundance of helium and deuterium we observe in ancient gas clouds, once again confirming that the rules guiding atomic formation have remained consistent across epochs. It's worth noting that our place in the cosmic timeline may offer a privileged vantage. The universe is old enough to have seen multiple generations of star formation, scattering elements across galaxies, but not so old that galaxies have dimmed into a dormant state. We occupy a slice of cosmic history where there's still plenty of stellar activity, supernova explosions, and robust chemical enrichment. Future astronomers, living trillions of years from now, if such observers exist, may see a very different universe, one in which distant galaxies have redshifted beyond visibility and local structures have decayed or merged. To them, the story of atoms might appear simpler or more obscure, as many of the bright cosmic signals we currently measure would be lost to cosmic expansion. Such reflections highlight our brief yet potent window for discovery. By capturing light from across space-time, we piece together a coherent narrative of how atoms took shape, how they formed stars and galaxies, and how those structures transformed over billions of years. It's an extraordinary endeavor, one that unites quantum-scale physics with grand-scale cosmology, melding laboratory experiments with deep-sky surveys. The philosophical implications run deep. If the formation of atoms and their subsequent evolution into complex chemistry is a cosmic inevitability, then life based on such chemistry might be a recurring theme across galaxies. On the other hand, if the balance of forces or constants were slightly off, atoms might never have stabilized, or stars might burn out too quickly, leaving a sterile universe. That fine-tuning raises questions about whether our universe is one among many, each with different parameters, some lifeless, others teeming with possibility. While such multiverse ideas remain speculative, they underscore the sense of wonder that arises when we see how precariously reality balances on the nature of atomic bonds. In contemplating these cosmic scales, we might find renewed appreciation for the mundane. The glass of water in front of you, the iron in a skyscraper's beams, or the silicon in a computer chip all trace their origins back to nuclear reactions in stars or earlier cosmic epochs. This continuity links the everyday world to processes spanning light years and eons. Each atom in your environment whispers of an ancient lineage shaped by collisions, heat, and time. All of which brings us back to our central narrative. Atoms built the universe. They formed under extreme conditions, survived epochs of expansion, found refuge in the cradles of star formation, and eventually sparked the chemical complexity that led to life. Even in the midst of unknowns, dark matter, dark energy, cosmic inflation, the essential role of atoms as the visible, tangible scaffolding for cosmic evolution remains clear. They are the protagonists of a grand saga, forged in the Big Bang, refined in stellar crucibles, and ultimately woven into everything from the simplest hydrogen cloud to the consciousness that now reflects upon this cosmic heritage. This sense of cosmic kinship might be the episode's core message, that in recognizing how atoms built the universe, we recognize a shared tapestry that enfolds galaxies, planets, and living beings in one continuous thread of matter and transformation. If we look close enough, through telescopes, microscopes, and equations, we see that thread woven through every facet of existence. And that, perhaps, is the most profound takeaway from exploring how atoms became the architects of reality. If we take a step back and examine what makes each stage of cosmic evolution possible, we discover a common theme: transition points. These are pivotal moments in the universe's timeline when atoms undergo transformations that fundamentally alter how matter organizes itself. The first big transition occurred when quarks combined into protons and neutrons, enabling the creation of stable nuclei within minutes of the Big Bang. Another pivotal moment came when electrons finally attached to those nuclei, giving rise to neutral atoms. Later, when pockets of gas collapsed under gravity, stars burst into life, commencing an era of stellar furnaces that shaped the chemical makeup of galaxies. One might call these junctures gateways through which matter moves from chaos to order, or from one form to another. Each gateway demands certain conditions. For protons and neutrons to form, temperatures had to drop below an extreme threshold. For electron capture, recombination, to unfold, the universe needed to expand and cool for nearly 380,000 years. For star formation to begin, density fluctuations had to gather enough mass to spark nuclear fusion in the dark cosmic seas. At each gateway, atoms, whether newly formed or evolving, were key players in driving the universe toward higher complexity. Within stellar cores, we see another kind of gateway, the threshold between fusing light elements, like hydrogen and helium, and forging heavier ones such as carbon, oxygen, and iron. This hinges on the balance of temperature, pressure, and nuclear cross-sections, how easily nuclei combine. Once a star burns through its initial hydrogen, it must either contract and heat up enough to fuse helium or collapse if it lacks sufficient mass. In massive stars, fusion steps through the sequence of increasingly heavy nuclei until iron is reached. Past iron, fusion consumes more energy than it yields, so the star's life teeters on the brink. Eventually, a supernova or core collapse can hurl precious metals across space, seeding molecular clouds that will birth new stellar generations. These episodes underscore the remarkable sensitivity of cosmic processes to fundamental constants and conditions. A slight shift in nuclear force strength could have prevented helium from forming so abundantly, or might have changed how quickly stars burn their fuel. The intricacies of quantum mechanics, which govern how electrons orbit nuclei, allow atoms to form stable bonds, enabling the diversity of molecules in environments like Earth. Alter one parameter, and the cascading effect might render the cosmos barren of the complex chemistry we take for granted. This leads some physicists and philosophers to talk about the anthropic principle, the idea that we observe these precise conditions because we exist to notice them. While such reasoning can veer into philosophical territory, it stems from a concrete observation. Our universe's physical laws permit atoms not only to form, but to coalesce into structures capable of reflection and inquiry. Regardless of how one interprets it, the fact remains that atoms serve as the bedrock of this existential puzzle. They are the tangible manifestation of cosmic order, each nucleus held together by forces that, if tweaked, might have yielded a universe where life never emerged. Meanwhile, our telescopes and detectors keep refining our picture of this grand design. Observations in gamma rays, X-rays, ultraviolet, visible light, infrared, and radio waves reveal distinct facets of how atoms behave in different energy regimes. X-ray data might spotlight high-temperature plasmas swirling around black holes, while infrared surveys expose hidden star-forming regions cloaked in dust. These multi-wavelength techniques stitch together a unified story. Atoms permeate the universe in myriad states, from the frigid molecules in dense clouds to the million-degree ions around energetic quasars. In laboratory settings, scientists go further by isolating single atoms or cooling them near absolute zero to observe quantum effects that vanish at higher temperatures. Such experiments highlight the uncanny dualities of matter, where electrons act like both particles and waves, and where atomic states can become entangled in ways that defy classical intuition. Though far removed from cosmic scales, these findings illuminate the microscopic rules that guide everything from how stars fuse hydrogen to how complex molecules bond in interstellar space. Another cutting-edge frontier is the study of exoplanetary atmospheres. Using spectroscopy, astronomers can discern the atomic and molecular lines in light that filters through or bounces off an alien planet's atmosphere. By identifying signatures of water vapor, carbon dioxide, methane, or even more exotic molecules, they infer the planet's temperature, chemistry, and potential habitability. This method rests on the reliability of atomic transitions, on the fact that under the same physical laws, each element absorbs and emits light at specific wavelengths. The cosmos becomes a grand lab, and atoms the universal language for decoding what's out there. Yet the universe remains replete with questions. What processes govern the birth of the largest black holes at early epochs? How did galaxies arrange themselves into the colossal structures we see in deep surveys? Why do neutron-star collisions contribute so heavily to certain rare elements? And is dark matter a yet undetected particle that interacts only gravitationally, or something more exotic? While atoms are central to the drama, these open problems remind us that there are layers to cosmic architecture that may lie beyond the realm of normal matter. Still, atoms' visible trail through the ages is nothing short of astonishing. By piecing together the puzzle, we find that each cosmic generation refines the matter at hand, forging new elements and scattering them. Galaxies act as arenas where these transformations unfold, and star clusters are the neighborhoods where matter recycles from one star's demise to another star's birth. Echoes of the Big Bang's initial conditions remain discernible in the background radiation, while the footprints of stellar nucleosynthesis show up in every planet's composition, our own included. Despite all we've unraveled, it's worth remembering how recently humanity discovered the truth about atoms. For most of human history, the realm of the very small was hidden. Ancient philosophers speculated about indivisible particles, but lacked the means to prove their existence. Only in the last century or so have we truly harnessed atomic knowledge, unraveling nuclear physics, building particle accelerators, and applying quantum mechanics to everything from semiconductors to lasers. And it's been just a few generations since we recognized that stars fuse elements in their cores, bridging the once impossible gap between terrestrial chemistry and celestial objects. Reflecting on our cosmic vantage, we see that we live in an era teeming with data, telescopes that sample the electromagnetic spectrum, gravitational wave observatories that detect merging neutron stars, neutrino detectors peering into the sun's inner workings. Every instrument testifies to atom centrality. We measure signals that originate in atoms or in the fundamental interactions that shape them. The cosmic timeline, from the Big Bang to today, emerges with ever-increasing clarity. Though we've come far, surprises still lurk. Dark matter might one day be shown to connect more intricately with atomic matter than we suspect, or a revised theory of gravity might tweak our assumptions about cosmic expansion. Fresh revelations could arise from deep underground labs searching for proton decay, testing whether matter itself is stable over eons, or from advanced telescopes capable of imaging exoplanets in enough detail to spot continents or oceans. With each discovery, the saga of atoms building the universe gains new chapters, possibly challenging or refining our existing frameworks. Ultimately, it's that dynamic quality, the interplay between known physics and undiscovered territory, that keeps the story alive. Atoms remain our trusty guide, bridging cosmic extremes. The scorching birth of protons and neutrons, the calm assembly of neutral hydrogen, the fiery forging of heavier elements, and the hush of deep intergalactic space. We observe them forming, breaking, recombining, and cycling through star systems, unveiling not just how matter endures, but how it transforms the universe in the process. If there is a single takeaway from tracing atoms through cosmic time, it's that emergence of galaxies, stars, planets, and possibly life depends on a delicate union of conditions. Atoms facilitate that union by providing the fundamental building blocks for complexity. And we, as observers, stand at a nexus point, shaped by these same atoms, yet gifted with the faculties to look back and understand how they came to be. In this grand interplay of forces, structures, and chemical evolution, we find ourselves woven into the cosmic fabric, both spectators and participants in the ongoing story of matter itself. Contemplating the universe's grand past leads naturally to speculation about its far future. If atoms built galaxies and powered stars for eons, what becomes of them as the cosmos continues to evolve? Observations reveal that star formation has already peaked several billion years ago. Galaxies today form fewer stars than they once did. Gas reservoirs dwindle with each stellar generation, as more matter becomes locked in long-lived stars, stellar remnants, or black holes. Dark energy accelerates the expansion of space, pushing galaxies apart so swiftly that given enough time, only the most local clusters will remain visible to one another. In such a future, starbirth might trickle to near zero, leaving behind dim red dwarf stars and faint embers of once luminous systems. Even on these smaller scales, the interplay of atomic physics and gravity ensures that matter undergoes continuous recycling until raw materials become scarce. White dwarfs and neutron stars might outlast everything else, harboring their exotic states of matter across unfathomable spans. Over trillions of years, cosmic stellar populations could dwindle to dark cinders. Yet atoms, or their constituent particles, would still persist, albeit in a quieter, cooler universe. Some cosmologists envision an epoch when black holes dominate the scene. In that extreme era, any lingering matter might gradually be pulled into singularities or dispersed as Hawking radiation. Depending on how one interprets quantum theory, even black holes might eventually evaporate, returning their contents to an ever-thinning cosmic background. This ultimate fate of matter hints at questions that straddle physics and philosophy. Do protons have an infinite lifespan? Many grand unified theories predict a tiny but non-zero probability that protons can decay, turning them into lighter particles over immense timescales, possibly 1034 years or beyond. While no decay has been definitively detected in experiments, the possibility remains open. If true, then even atoms aren't forever. They would gradually vanish, leaving the universe a realm of photons and subatomic debris. Such a vista might feel bleak, but it's also a testament to the unrelenting evolution that began with quarks binding under ferocious heat and pressure. The cosmos may be dynamic, not just in its early youth but across all ages, concluding in an era of bare quantum whispers rather than stable structures. All these lines of thought point toward our incomplete grasp of fundamental physics. We possess a powerful framework, Einstein's relativity for gravity and the Standard Model for quantum fields, that explains nearly all observed phenomena involving normal matter and energy. Yet dark matter and dark energy remain mysterious. Could they be explained by adding a new particle to the Standard Model, or do they require a radical rethink of gravity itself? Physicists at facilities like the Large Hadron Collider continue searching for signals of supersymmetry or other new physics that might yield a dark matter candidate. But so far, nature keeps its secrets well guarded. A deeper unification of quantum mechanics and gravity also stands on the horizon. Both frameworks are incredibly successful in their domains, yet we lack a seamless theory that integrates them. If such a theory is found, some propose string theory, others loop quantum gravity, or more recent ideas, it might revise our understanding of how atoms first formed and whether matter could manifest in states beyond what we observe. Perhaps it would also clarify whether the Big Bang was truly the beginning or simply an event in a larger cosmic cycle. Answers to these conundrums would reshape the entire conversation about how atoms emerged and what final forms they might take over unimaginable timescales. Meanwhile, astrophysicists refine simulations to incorporate everything from microphysical plasma processes to the collective gravity of galaxy clusters. The hope is to replicate key events, like the ignition of the first stars, the coalescence of supermassive black holes, or the birth of spiral arms, and match these virtual universes to telescopic data. Time after time, such simulations reaffirm that atomic matter, though just a fraction of the total cosmic budget, performs essential functions. It radiates light, forms chemical bonds, and drives feedback loops. Were it not for the complexity that atoms allow, molecules, dust grains, magnetic fields, and more, we would lack the vibrant tapestry of stellar and galactic evolution that make the cosmos so captivating. Those same complexities ripple into biology and intelligence. The fact that atoms can arrange themselves into self-replicating molecules, harness energy through chemical reactions, and eventually yield neural networks capable of insight. This alone could be viewed as an extraordinary triumph of cosmic potential. From a vantage of cosmic time, Life is a recent and possibly fleeting phenomenon. Yet on Earth, it has transformed the planetary landscape and even begun to reach beyond, launching spacecraft that carry earthly atoms out of our home system. Still, for all our advanced instrumentation and theoretical models, the bulk of cosmic matter, dark matter, remains invisible to direct detection. We know it fosters galaxy formation, shapes gravitational wells, and affects large-scale structures, but the exact nature of its particles, if they are particles at all, remains elusive. Some theories propose weakly interacting massive particles, WIMPs. Others posit axions or sterile neutrinos, and a few suggest modifications of gravity. If dark matter is indeed a novel particle, that discovery will be akin to unveiling a new dimension of how matter organizes itself, expanding our definition of atoms to encompass or contrast with previously hidden building blocks. As we conclude this journey through the universe, consider this chilling truth. Everything you see, everything you are, began as fragments of chaos forged in the explosive fury of the Big Bang. As for dark energy, it might be a vacuum energy intrinsic to space itself, or a dynamic field that changes over time. Either way, its repulsive effect appears to drive galaxies apart at an accelerating pace. If this trend endures, future civilizations might see fewer galaxies within range, limiting their window into cosmic history. Perhaps they will have to rely on ancient archives or advanced gravitational wave detectors to reconstruct what we now observe directly. In that sense, the moment we inhabit, replete with visible galaxies, robust star formation, and detectable background radiation, seems almost like a sweet spot for learning about how atoms forged a cosmos so rich in phenomena. All told, the tapestry of cosmic evolution can be understood as a saga of matter under pressure, guided by fundamental forces, and orchestrated over epochs spanning from the immeasurable density of the Big Bang to the quiet hush of a future dark cosmos. At each juncture, atoms bring forth new layers of complexity, from hydrogen and helium gases to star factories of heavy elements, from interstellar chemistry to planetary biospheres. Even if dark matter, dark energy, or new physics add chapters we haven't fully grasped, the visible portion of the universe, atoms, remains our most direct window into cosmic origins and destinies. As we refine this understanding, we're reminded how each step depends on the previous. If quarks had never formed stable nuclei, there'd be no stars. If supernovae hadn't synthesized heavier elements, there'd be no biology. If Earth had formed too close or too far from the Sun, life here might never have arisen. The chain of contingencies is long, and each link underscores the resilience and adaptability of atomic matter. It's no exaggeration to say that every breath you take, every cell in your body, and every twinkling star overhead traces its lineage back to a near unfathomable cosmic dance that began almost 14 billion years ago. Where does that leave us today? We stand amid an era of discovery, bridging quantum insights with deep space observations, peering back to the first epochs of star formation, while also pushing the envelope of particle physics. We might not hold all the answers yet, but the journey to uncover them, a journey that tracks the path of atoms across time and space, continues to shape our perspective on who we are. In seeing ourselves as part of this long heritage, wrought by thermonuclear fire and gravitational scaffolding, perhaps we glean a sense of continuity that unites the ephemeral present with both the ancient cosmos and its eventual future. The story, in short, remains unfinished. Atoms built the universe we know, but that process of building is not static. It's a rolling narrative, each new stellar generation, each merging galaxy, and each cosmic revelation adding its voice to the symphony. We are witnesses, and in subtle ways, participants. For the atoms in our bodies, forged in distant stars, now shape thoughts, inventions, and explorations that feed back into how we steward this planet and envision our place in the cosmos. If there is any testament to the power of atoms, it is that they do far more than shine in the night sky. They also illuminate the pathways of our own curiosity. Another way to appreciate the magnitude of this atomic journey is to consider how it manifests in everyday phenomena. Look around. The calcium in your bones, forged in stellar cores eons ago, now supports your every step. The iron coursing through your blood came from a star's dying gasp, ensuring that oxygen can reach every cell. Even the carbon in the simplest leaf has been passed down through countless cosmic cycles, enabling the photosynthesis that underpins so much of life on Earth. None of this would be possible without the remarkable stability and versatility of atoms. Yet we often take atoms for granted. They seem so ordinary that we rarely stop to ask where they came from or how they managed to hold together. Only when we glimpse them at extremes, like in nuclear reactors or high-energy experiments, do we sense their fierce power. Or, on a cosmic scale, we watch them ignite in stellar furnaces, lighting galaxies with the glow of fusion. These extremes reveal what atoms are capable of, underscoring their role as both the simplest units of matter and the engines of nearly every grand cosmic event. For science communicators and educators, showing how atoms unify distant galaxies and local biology is one of the most potent ways to spark a sense of awe. Children in a classroom might handle a piece of meteorite, realizing it's older than Earth itself, or gaze at a star chart that highlights the hydrogen lines in distant stellar spectra. Such moments can plant the seed of curiosity that grows into a lifelong appreciation for astronomy and physics. After all, we're dealing with the very building blocks of existence, something that transcends cultural or national boundaries. Anyone, anywhere, can look at the stars and know that those pinpricks of light share the same fundamental ingredients as the molecules in our bodies. If there's a broader takeaway from this exploration, it might be humility. The forces that shaped atoms and guided them into stars, supernovae, and galaxies are astonishingly intricate. Our vantage point, here on a small planet orbiting an ordinary star in the outskirts of a typical galaxy, is both modest and uniquely privileged. We happen to live during a phase of cosmic history when star formation is still robust, background radiation remains detectable, and galaxies have not yet receded beyond all detection. That gives us an exceptional window to piece together the puzzle of our origins. But humility goes hand in hand with responsibility. As we harness atomic processes, be it nuclear power or advanced materials, we wield part of the cosmic toolkit that built the universe. Our actions can reverberate through ecosystems and economies, shaping the very future of planetary life. When we manage these resources responsibly, we echo the cosmic symphony of atoms transitioning and evolving in a coherent dance. When we misuse them, we risk fracturing the delicate balance that permits life to flourish. The same can be said of our pursuit of knowledge. Telescopes, accelerators, and satellites don't just satisfy curiosity. They help ensure we remain informed stewards of a world shaped by cosmic processes. By measuring how atoms behave in extreme conditions, we improve everything from energy production to space exploration. By studying distant galaxies and supernova remnants, we refine our models of climate and planetary formation, giving us insights into Earth's own future. In a sense, we leverage the same matter that formed us to uncover how and why it formed in the first place. Looking forward, space missions aimed at asteroids and comets might shed more light on how these smaller celestial bodies contributed to planetary chemistry. Samples returned from these objects can reveal the isotopic fingerprints of early solar system material, an echo of interstellar processes that predates our Sun. Meanwhile, missions to icy moons in the outer solar system push the question of whether life's building blocks can thrive in subterranean oceans far from traditional habitable zones. Once again, we see atoms as the currency of cosmic possibility, forging complex molecules even in environments alien to our terrestrial sensibilities. We might ask, too, about the philosophical resonance of this grand narrative. If our reality emerges from the interplay of quarks, electrons and fundamental forces, does that make our experiences, love, wonder, ambition, merely byproducts of atomic interactions? Or does it elevate them? Perhaps knowing that our deepest emotions and loftiest dreams are encoded in patterns of star-forged atoms imparts a sense of cosmic dignity. Far from being merely matter, we are matter that has become aware of itself. Atoms coalesced into a form that can contemplate its own origins, a rare and remarkable twist. Such reflections can serve as a bridge between science and other domains like art, religion, or philosophy. Throughout history, creation myths have tried to explain how the world arose from chaos or was shaped by divine forces. In modern cosmology, we have a different tale, one of a universe spontaneously expanding, cooling, and crystallizing into atoms, stars, and galaxies. It's a narrative grounded in observation and theory, yet it evokes wonder akin to the most ancient stories. The difference is that we can test and refine our cosmic account, matching it to evidence gleaned from cosmic background radiation, stellar spectra, and the distribution of galaxies. Each new observation or experiment either confirms or adjusts the storyline, continually tuning our understanding. Even so, the story needn't cancel out the sense of transcendence many seek in life. Rather, it invites us to find awe in the very real processes that carved the channels of cosmic history. If anything, comprehending how atoms built the universe can deepen reverence for creation's vastness and complexity, showing us that reality is in many ways more astonishing than our ancestors could have imagined. And it's not finished. The cosmos remains a work in progress, with stars still birthing elements, black holes still colliding, and dark energy still warping the grand scale of existence. As we near the conclusion of this episode, it becomes evident that the topic of how atoms built the universe spans countless sub-themes, from the earliest quark soup to the destinies of star systems, from the chemistry of life to the edges of known physics. We've traversed a sweeping arc of time, from the Big Bang's first fractions of a second to speculative epochs trillions of years into the future. At every turn, atoms serve as constants in the cosmic equation, symbols of resilience and potential. Whether you're peering through a microscope or gazing at a nebula through a telescope, you're witnessing the same fundamental building blocks at work, transformed by context, yet guided by the same unchanging laws. It's a narrative that can bring us comfort in times of uncertainty. No matter how tangled daily life becomes, the cosmos flows on, forging and reforging matter in cycles beyond our immediate grasp. At the same time, it can spur us to think more expansively. After all, if atoms can do all this, if they can fuel stars, craft worlds, and even generate conscious minds, what else might be possible as time unfolds? Thus, we arrive at a simple but profound realization. The universe is not an indifferent collection of random particles. It's a grand stage where matter organizes into forms ever more intricate, culminating, at least here on Earth, in beings who can look back and marvel at the process. In that marvel lies the impetus to explore, to learn, and perhaps to shape a small part of the cosmic destiny ourselves, guided by the lessons atoms have been teaching since the dawn of time. In considering how atoms built the universe, we have journeyed across nearly 14 billion years of cosmic history, tracing a line from the searing brightness of the Big Bang to the quiet possibility of distant worlds. Atoms are the silent connectors through time and space, birthed in those first moments of cosmic expansion, refined in stellar furnaces, and woven into galaxies, planets, and ultimately into us. Every cluster of galaxies, every flash of a supernova, every crashing wave on an ocean shore carries an echo of that ancient lineage, shaped by the interplay of gravity, nuclear forces, and quantum rules. We stand here at a crossroads of knowledge and wonder. On the one hand, science has laid bare so many details: the exact spectral lines that reveal what stars are made of, the cosmic microwave background confirming a fiery origin, the delicate processes that allow carbon, oxygen, and iron to form. On the other, mysteries endure: dark matter, dark energy, the unification of gravity with quantum physics, reminding us that each answer opens new doors of questioning. Yet through it all, atoms remain our steadfast companions, bridging epochs and environments in ways both humbling and heroic. At the broadest scale, these atoms have sculpted a universe capable of seemingly endless variation. Some galaxies brim with star formation, glowing vividly in ultraviolet bursts. Others are quieter, massive elliptical hosts to older stars. Countless smaller dwarf galaxies pepper the cosmic web, overshadowed yet integral in cosmic mixing. All revolve, merge, evolve, and shine, set against the backdrop of a darkening cosmos. Even if we fast forward billions of years, atoms will continue their dance, albeit in a stage altered by the relentless push of expansion and the dwindling fuel of star formation. On intimate scales, atoms have awakened as life, at least on Earth. A planet forged by cosmic dust has grown forests and coral reefs, harbored creatures that breathe and think, and even nurtured a species capable of launching satellites and glimpsing back at its homeworld. That single fact, that the universe can look upon itself through our eyes, embodies the grandeur of atomic potential. The same carbon that once floated in interstellar clouds now makes up the neurons through which you perceive and comprehend this story. Some might see in this narrative the imprint of cosmic destiny. Others might see the sublime interplay of chance. Perhaps the real power of the story lies in its ability to encompass both views. We can marvel at the staggering improbability of each step: protons forming, electrons binding, stars igniting, life arising, while acknowledging that once set in motion, the laws of physics can yield wonders we might never have imagined. Far from denying meaning, this perspective can instill awe in the raw creativity of matter and energy, shaped by fundamental constants that allow complexity to flourish. In a time when we often focus on immediate concerns, remembering the cosmic dimension can ground us. It highlights that we, like the universe, are participants in an ongoing process of transformation. Our choices, from how we harness energy to how we protect ecosystems, resonate within the planetary tapestry that atoms helped create. Though our human scale is minuscule next to galaxy clusters and eons of time, the same universal laws that power supernovae also power the chemical bonds in our bodies. The universe has entrusted us with a fragment of its essence, which we can either nurture or squander. Stepping back to cosmic perspective once more, we are left with an overwhelming sense of unity. Every star shining overhead, every atom in your body, and every grain of dust drifting in starlight shares a common origin. The differences between them, whether they're in a black hole's accretion disk or forming the wings of a butterfly, arise from the contexts in which they evolve. Yet the building blocks and the laws that govern them remain largely the same. In that sameness lies an extraordinary truth. The cosmos has a consistent, elegant grammar, and atoms are its letters. So when we say atoms built the universe, we're also saying that the smallest known structures hold the power to construct the biggest cosmic architecture. We're saying that from a few quarks bound together in the earliest seconds, we arrive at towering galaxies whose light journeys billions of years to meet our gaze. We're saying that matter, under the right conditions, can learn to think and dream. These revelations invite us not just to memorize facts, but to feel our connection to the vast processes that span cosmic time. Knowledge becomes reverence when we let it shape our perspective on existence itself. Some chapters of this story remain unwritten. Scientists continue to refine how galaxies form, how supermassive black holes ignite, and what hidden secrets dark energy might conceal. Perhaps new instruments or genius insights will reveal that the scaffolding of matter is even more intricate than we imagine. But for now, the pieces we do see offer a majestic puzzle. Atoms are the universal currency of creation, forging everything from cosmic dust to living consciousness. At the end of our tale, we find ourselves part of a lineage that began in the birth cries of the universe. Our impulses to explore, invent, and reflect are acts of cosmic self-discovery, propelled by matter that once burned in suns before settling into the structures of our hands and minds. If there is a more powerful illustration of how atoms built the universe and continue to build it, one would be hard-pressed to find it. In drawing this journey to a close, let us remember that each star in the sky, each planet turning silently in its orbit, and each spark of life is a chapter in the story of atoms. It's a story still unfolding in real time, both out there among the galaxies and within us, in every breath we take. And as that story goes on, we stand ready to observe, to learn, and perhaps, in our small way, to guide how these building blocks move forward. Thank you for joining us on this extraordinary journey through the cosmos here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.